I've talked a lot about how there are vectors don't behave like numbers. So we're going to really start to see that as well today. And we've already talked about multiplying. Oh, so these are the three products involving vectors. And what I talked a lot about was how it's really important, and today there's part of the practice will cover this. It's really important that you know when you perform an operation on vectors, what's the outcome? When we talked about numbers, just numbers, which you've been talking about for years and years and years, I mean, the outcome is always a number. It might be positive, it might be negative. That's something you talk about, when you multiply a positive times a negative. What's the outcome? You get a negative. So that is something you've seen before, but it's always numbers. But with vectors, that's not the case. And there are times where you might try to be doing something, or you might be making something up that doesn't exist. So it's really important that you understand what the output of the different operations are. So who can tell me when you multiply a vector by a scalar, we've already seen this scalar multiplication, what's the outcome? A vector. Okay? So that's important to know. So we've talked about multiplying by a scalar. Today we talk about dot product. Next week on Tuesday we'll talk about cross product. So here's a definition, or one of the two definitions of the dot product for vectors A and B. A dot B, you can't say A times B, because that's not defined. You can't change it. You can't change the dot to brackets or something else. Like, it's called the dot product for a reason. So we call it A dot B, or taking the dot product of A and B, or take the dot product of two vectors. You can't say I'm going to multiply these two vectors. Undefined. We don't multiply vectors. People might say, why? Why can't you just multiply the x's, multiply the y's, multiply the z's? And I would say, well, I don't know. What does that mean? Like, what would it mean to do that? What would be the outcome? You'd get a vector. What does that vector mean? I think nothing. Try it with some vectors if you want, and like graph them. You're like, there's no relationship as far as I know. So like, it's not a thing. So you have to have definitions for operations. The problem is you've been doing most of these operations for so long, the definitions are obvious and intuitive and straightforward to you, like multiplying two numbers. You just know what that means. But those definitions don't work with vectors. So we have to come up with new ones. And they have meaning, and I'm going to try to share that meaning with you, but it's not easy, because until you get deeper into this, I don't think it's obvious what the dot product is actually doing and why it would be useful. And then when we get to the cross product, I think it's even harder. So bear with me. Recognize that if you went further with this and you got into more work with vectors, you would eventually get to a point where the dot product was as intuitive to you as multiplication is, a multiplication of numbers, right? But we probably won't get there. But I'll give you some examples that will hopefully shed some light on what the dot product is, what it does. At any rate, this is what the dot product is. A dot B equals the magnitude of A times the magnitude of B times cosine of theta, where theta is the angle between A and B when they are tail to tail. As we've talked about, vectors don't exist in particular positions, so two vectors could be anywhere. But if I took them and put them tail to tail, theta would be the angle between them. From this point forward, I will no longer define theta. When you see a question that says theta equals this, you have to know that that's the angle between the two vectors tail to tail. The only time we would ever change that variable up to alpha or something, which I don't think we ever will, but if we did, it would be with a diagram, and we would mark the angle in the diagram, and then you could use a different one. But otherwise, if it's just theta, you're like, well, what's theta? No, we know what theta is in the context of these vectors and these questions. It's the angle between them when they're tail to tail, okay? And that's what that is. What is the magnitude of A? Not what is it specifically, because it's not defined, I know, but like, how is it represented? What's it like? A length, which is like a number, right? It's a length of something, and the length of something is just the number, like 5. So the magnitude of A is a number. Magnitude of B is a number. Cosine of theta is What? Huh? A number, right? Cosine of pi by 2. Cosine of pi. Cosine of pi is -1. A number. A number times a number times a number is going to be a number, not a vector. Look at that. The result of the dot product is a scalar. This is what I'm talking about. This is interesting. Imagine 3 vectors, A, B, and C. What if I did this? A dot B plus C. Huh? It would be a vector? So what's that? How do you add a vector to a scalar? Who remembers how to do that? Nobody, because we never defined it. It's not a thing you can do. Did we ever add a scalar to a vector? Again, would you add it to each of the components? I mean, you could. Would that be useful? I don't think so, because I don't think it's a thing that we do. It's not a defined operation. You can add 2 vectors, and there's a meaning to that. It gives you the resultant of those vectors tip to tail. But adding a vector to a scalar isn't a thing that we can do. So this is undefined. So this is the kind of question, and I hope it's not one of the actual questions. If it is, I just gave you the answer. But this is the kind of question that you would get. What's the result? The result would either be a scalar or a vector, or it's not possible. It's not a thing that's defined. What if I did this? Why? So this results in a scalar, and you can multiply by a vector. So this would result in a vector. Again, I hope that's not one of the homework questions, which is different from this, which is also undefined. Because that's just, I guess, multiplication. And you can't just multiply 2 vectors. You have to talk about the type of product that you're taking. Okay, so that's what I mean. But everybody's wondering, what is the dot product? Well, first of all, I'm going to explain it in one way, then we'll talk about some examples. I'm going to explain the formula a little bit. It's pretty straightforward. Like I say, then we'll talk about some examples. That should clear things up. So the dot product is when you project one vector onto another and multiply the magnitudes. That is the definition of the dot product. Turns out the formula we already saw accomplishes that. But why? What do I mean by project one onto another? So I'm going to do 2 vectors here. I should have made that more. Be a little bit easier to draw if we make this line horizontal. What do you think it means? What does it sound like it means to project one onto the other?
Like if you mentioned that there's a light above it, then the shadow cast by A onto B would be projected.
Did you just make that up?
Yeah.
Wow, impressive. That's exactly how I would describe it. Imagine having a light shining directly over top of A, the shadow that A would cast onto B. Now, you could project either one onto the other. It won't make a difference. We'll talk about that more after. But the other way, so if I take this down to a right angle to there, this becomes my new length. We'll call it C for now. That length is like a magnitude. And the dot product is if I take C times the magnitude of B. So it has no direction because you're just multiplying magnitudes. It looks like it would be in the magnitude of B, but I could project B onto A as well, even if at a right angle it missed, which in this case I think it wouldn't. It's harder to do on an angle like that, but even if it misses, we'll see this a little bit later, you can project either one onto the other. So it has no direction because it's not a vector. It's just a scalar. Why does our formula work? So I want to start with the idea that what is cosine? Cosine of theta is adjacent, which is C, over hypotenuse, which is the magnitude of A. Not just A, the magnitude of A. So if I want to know what C is, I can bring the magnitude of A over. And if A dot B is C times the magnitude of B, then it's the magnitude of A cos theta times the magnitude of B, and obviously I can rearrange that into the form that we saw earlier. Right? So it's just C, the projection, times the magnitude of B to see how much bigger it gets. But what is C? It's just by SOHCAHTOA, right triangle trigonometry, it's magnitude of A times cos theta. Right? Pretty easy, pretty straightforward. No? Well, this rearranging, I mean, is straightforward. Yeah, like to see why the formula does this. Not straightforward why you would want to do that. What it accomplishes. Well, I'll clear that right up. It's a mechanical work is the dot product of force and displacement vectors. So there's one good one. Or it's the magnetic flux is the dot product of the magnetic field and the vector area. And power is the dot product of force and velocity. So 3 useful examples. Does that help clarify things? Yeah? I mean, you understand some of those words, don't you? You've seen them in physics class? Say that again? Yes. Where does this come from? That's just what it is. And you could use it if you're doing any of those things. Not satisfying? Yeah? What do you mean, where did I get the B from? This? Because that's what A dot B is, the projection of one vector onto another times the magnitude of the other. That's what it is. Like you can't ask where'd you get that? That's what it is. That's the definition of what it is. So that's what it is. I mean, it is what it is. But the real question you're all asking, but you don't know that you're asking, is what's the purpose of this? What's the usefulness? Like, why is that something you would want to do? And those 3 examples are supposed to help. I know they're not satisfying. So I'm going to give you a better one. And we're going to talk about Mario Kart for a second here. So if there's any Mario Kart aficionados, have you played Mario Kart before? I've played Mario Kart. You don't have to be shy. It's a great party game. I'm going to give you, if anybody is a true Mario Kart player, though, I always get people disagreeing with me and telling me I'm wrong. I didn't make this up. So I've been told this is not how Mario Kart actually works. I'm not entirely sure I agree, but fine. That's not the point. Whether it actually works this way or not, I think it will help you understand what it's doing. This is the only good explanation that I can give you. So, if you've not played Mario Kart, this is a speed boost pad that you can drive over, and it will give you a temporary boost of speed. Imagine it's the case where if you drive directly over it and your direction is in line with the direction of the speed boost, then you get the biggest boost. You get more of a speed boost. See, people shake their heads. They think it's not true. I don't know that you actually know that that's the case. I'm going to challenge you on that this is anecdotal in your case because you've only played it and you think, oh, well, I think that, but blah, 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 whatever. Unless you're measuring it, don't talk to me. Yeah, that's true. If I go over it sideways, and again, I'm not saying it pushes you in that direction. I'm not saying it at all. I'm saying it gives you a boost in your direction, but it's not as big of a boost. And I'm not actually claiming this is how it works. I'm just saying imagine. Okay. And then if you drove over it perfectly perpendicular, I guess you'd get no boost. And then you're right. If you drove over backwards, what would happen? I don't know. Okay, but imagine if that happened. That's a good explanation of what the dot product is doing. If you're driving over it fully, you get a huge boost. You get the biggest boost. If you're driving over it on a diagonally, you get a boost relative to your angle. And it shrinks down to 0. That makes sense? Again, why you would want to do this? Well, there's a whole bunch of good reasons that we haven't gone far enough with any of this stuff to really connect with. So we can't worry too much about that. On the back of your page are some examples that I've drawn for you, so that's a bit faster. After that, we're going to do more examples you have to write down. Yeah?
It's like with the work thing, I think if people who've taken physics, I think it makes sense just because work, like, even if you're pushing on something but it doesn't move, then you've done 0 work to it.
Yeah.
So if the force is like, unless the force is actually making a move, which is the displacement vector, then you're going to get 0. So I think that kind of is like the displacement vector will be 0, so it's not cast shadows. So
Yeah. I think you're right. I think that's one that if you're very good at physics and you understand it, you could probably understand that particular example. And as well, you could think like, I don't know, if I'm doing work at an angle to the direction that I want or something, like, I don't know, yeah, but you could make sense that you don't get the full outcome of the work.
Yeah, we do a ton of questions that are like you pushing on a box like downwards with like a 45-degree angle.
Yeah.
And then like it's only the amount that is actually pushing forwards that you're actually using for the work.
Yeah, yeah. So I think you're probably on the right track there. Okay, let's do a few examples. Determine each dot product. So it's pretty straightforward. A dot B, magnitude of A times the magnitude of B times cosine of theta, which, as I said, is the definition. By definition, is the angle between them. So this is 30 times 40 times cosine of 50. Oh, very, very important, and this is tricky for our exam. Calc in degrees. Now, right? So during the exam, you're going to have to change your calculator if you're doing vectors and working in degrees, or if you're doing everything else that we've done, which is in radians. If questions like that show up. Turns out this is approximately 771.3. Oh, where'd you come from? Seems pretty big. What's 30 times 40? 1,200. So this is part of 1,200, not all of 1,200, because it's at an angle. Right? So that's how this works. If these, whatever they were, work or whatever they were, if they were in line with each other, you'd be getting the full amount of extra speed boost, Americard, whatever, of 1,200, but you're only getting part of it. Okay, I want you to try this one on your own. So get out your calculator if you didn't already. I mean, this is so easy, right? Like you're multiplying 3 numbers together, my gosh. What do you get? Who's got an answer? Who's got an answer?
Negative 1,895.
8. Negative that 8. Thank you. 99.5. Does it make sense that it's negative? Well, cosine of 125 is in quadrant 2. Cosine is negative in quadrant 2, so that's going to be a negative number. It makes sense. And as well, if I think about projecting this vector onto the other vector, I'm actually projecting it onto the other vector, like I guess sort of in the other direction. Like like they're working against each other. That actually does make sense, I think. And this one's a little bit hard to do, but I'm going to try. So if I extend this and I project this one down to a right angle to that one, again, it projects to the other side of it. So they're working against each other. So it's a negative value. So it turns out that makes, I think, sense, and that is the way that it works. Okay, one more. Try this one. Zero. Did you do that in your head? You just thought about it. Yeah, very good. If you project a light, you get no shadows. You're multiplying by 0. But also the cosine of 90 is 0. We know that from the graph. And there's no, yeah, it makes sense from the examples that we've done that it would be 0. Okay, this is very important, by the way. You might be asked a question like, how would you know if two vectors are perpendicular or something like that? This is one of the things that you just need to know. Another one of these little things that you need to know. So you don't have this page, so you got to do it on another piece of paper. Some properties of the dot product. Notice that this is important that it's for non-zero vectors, because if a vector was a zero vector, it would have 0 magnitude, and that kind of throws all of this out the window, because when you multiply by 0, it would always be 0. So as long as they're non-zero, then A dot B equals 0. I don't know why I'm writing it way over here. A dot B equals 0 if, remember this is if and only if A is perpendicular, vector A is perpendicular to vector B. What does that if and only if mean? It means if they're perpendicular, their dot product will be 0, and it means if their dot product is 0, then they are perpendicular. It goes both ways. And there can be problems that you would solve going both directions. Does that make sense? If they're perpendicular, their dot product is 0. If their dot product is 0, they are perpendicular. Okay, A dot B equals formula. Remember, these are just numbers. 2 times 3. Do you all agree that 2 times 3 is the same as 3 times 2? Always. It's property of multiplication. So this is equal to, which is equal to what? What does that look like? There? No? B dot A. Okay, so A dot B is equal to B dot A. And you're like, well, of course it does. That's how it works. So I'll remind you, no, it is not. Vector operations do not follow necessarily all of the properties that numbers follow with their operations. So it's true of multiplying numbers. Turns out it's true of dot product, but it's not true of all the operations with vectors. Yep.
Can you apply dot product to three vectors?
No, because this would be a scalar, and if you tried to dot it with another vector, can't do that. A dot A. Magnitude of A times the magnitude of A times what? Cosine of 0, right? A in itself, there's no angle between them. The angle between them is 0. What's the cosine of 0? 1. So what is this? Magnitude of A squared. You could recreate that one. You don't have to memorize that one, but it's a useful one to know. Okay? And I'm just going to tell you these two. We're not going to prove them or define them or derive them or anything like that. So it is distributive. And it is associative. I want to say those properties, we talked about distributive and associative in terms of other things with vectors. I want to say that's not going to be a big part of the stuff that we do. So, I mean, if you had to memorize all the ones that were distributive and all the ones that weren't, that would be a lot. You probably won't really have to. We're not going to try to trick you that way. We're more interested in those little questions like, is this possible? Where you just think, well, yes, it works out. No, it doesn't. Those are the ones that we're more interested in. But to remind you that in some cases these properties hold and in some cases they don't.
For number 4, like the reason is pretty simple, right? Because like any vector can be with another vector.
Yeah, you're right. Like to you, it's intuitive. You mean it makes sense. You could do B plus C and then you could dot it with A, and if you did the sort of visual of that, if you graphed it, yeah, it would make sense, I think. Okay, a couple of examples using these. So this is going to be distributive. So this is going to be ku dot u, but again, I can use one of those properties to write this like this, ku dot u plus ku dot v. I can either write it like this or like this. You know what I mean? So this turns out as k u squared plus k u dot v. Whether you wrote this one like this or like this, one's not more simple than the other, so I wouldn't overthink that kind of stuff. It's just showing what's possible, I guess.
Does the property also work with like I hat, J hat?
Yeah, absolutely. I mean, those are just special vectors. So anything you can do with a vector, you could do with those vectors. Absolutely. Seema, did you have a hand?
Yeah, how does will
Huh? This one?
Yeah.
Because we saw earlier that u dot u is the magnitude of u squared. We just saw that. So that's one that if you ever had that, you should simplify it to that. But if you just took the dot product of those, remember, you could work that out. Okay, and this is something that you may not have thought of in a while, but this is two binomials dotted. And binomial is just distributive property twice, where I take this and I distribute it, and then I've got this times this, so I redistribute that back. Right? That's all that binomial expansion is distributive property types. We don't teach it that way, we don't think of it that way, but that's what it is. So in other words, this is like just a regular binomial expansion. Whoops, forgot to plug in. Right? Regular binomial expansion. Shouldn't be now. So this works out to u dot u, u plus u dot v minus v dot u minus v dot v. Well, we already saw that u dot u and v dot, u dot v and v dot u are the same. One's positive and one's negative, so those are going to be gone. So I mean, nicely. I'm sure that this is stuff that somebody uses if you're working with vectors a lot, not what we'll use a lot. Doing this kind of stuff. Good practice for the properties. Any questions? Oops. Okay, for my next trick, you're going to need probably 11 or so lines. So you may want to start a new page if you're working at the bottom of your page, or if you write big, or if you like to leave double space or something like that. You need 11 to maybe 15 lines. Also depending on how big you draw that diagram. If you can make that diagram take up 3 lines, and you probably can't, right? If it carries on to the next page, it's not the end of the world. We're going to derive this. Oh, we're going to derive not the dot product that we already saw. We already saw that. We like working with Cartesian vectors. They're so much more useful. Sure, you might be given like those examples that we saw with the 30 and the 40. Sure, in real life, you might know that little Johnny is running in this direction at 3 meters per second, and little Billy is running 30 degrees from Johnny's path at 4 meters per second. That's something you might know. And then you can take the dot product between them. But, and in that case, you wouldn't know what direction they're running. You would just know that they're 30 degrees to each other. It's definitely something that you could know. Or if you know this one was going north and this one was going north 40 degrees east, they're at 40 degrees to each other. Like that stuff that people could do, but that's less what we do. More of what we do will be with Cartesian vectors because it's a nice system. So what is the dot product for Cartesian vectors? This is what we're going to derive. So we're going to start with, turns out, and a few things that we're starting with are just things that we need to know. So like if you were going to recreate this, you would want to know the first few steps and definitions that we're doing, and then the rest of it kind of just flows. Often that's how these things work. So we're going to start by making a vector that goes from the tip of B to the tip of A, and we're going to call it C. and we want to come up with what C is. And I believe this was in your practice somewhere, but we haven't done an example yet. So when I have something like this, the easiest way to start is how can I easily write one of the vectors in terms of the other two? Does anybody see a way you can do that? One of the vectors equals something to do with the other two. There's an easy one, if you can spot it.
Negative b plus a equals c.
Okay, good. Not the one that would work. Negative b plus a equals c. Nice. A equals b plus c. So that we'll start with that one, but you could start with yours too. So if I follow b, if I start at the tip of both of them, I follow b and then follow c. B plus c is the same as a. So we'll start with that. Oh no, I do want that color. Vector b plus c equals a. And then all I do is move b to the other side. And I get a vector for c, which is a minus b, which, Daniel, I think that's what you said, right? So you went straight to what we actually wanted, but which would be fine if you look for the easy thing, start with that, and then rearrange. So this is, we need some expression for vector c, so now we have one. We also want to have, because we're talking about Cartesian vectors, we have to define what they actually are. So we're going to define vector a. Now, don't write this down yet. I could define it as the x value of a, but I'm actually going to do it in a different way just because we can. It's still the x value of a, but a subscript x and a subscript y. And b is bx and by. And if that's true, that means C, which is a minus b, we've done this, subtracting vectors. You just subtract their horizontal and vertical components. So this is ax minus bx and ay minus by. So all of this is just stuff we're supposed to know and define before we even start. And we don't have to define this right now, but I'll just remind you, we're going to do a few of these. The magnitude of a is ax squared plus ay squared. Right? And we're going to need some more of those magnitude things, but we'll do the other ones in place. Does anybody see a nice relationship that we could start with that would be helpful given what we already know about dot product? Wild guess. Just curious. Anybody has an idea? Think about the formula for dot product and what's in there. And we have a triangle. Idea?
The sine law or cosine law, one of those. I don't remember either.
Okay, fair enough. Which one do you think we might want? Sine law or cosine law? Why? Because there's a cos in the formula. So very good. And that is exactly right. So I can remember it for us. And it is the magnitude of c squared. It's c squared equals a squared plus b squared minus 2ab cos c, right? But we have to talk about magnitudes because it's not just vectors. So it's the magnitude of c squared equals the magnitude of a squared plus the magnitude of b squared minus 2 magnitude of a, magnitude of b, cos theta. Cos c, but we'll do cos theta. Ha! What do you notice?
This looks like the a dot b formula, but see, when we were doing like proofs like this, aren't we supposed to like set some stuff as our principle like before solving these? Like,
Well, that's kind of what we did over here. And then given this diagram, this is true. Yeah. So A and B were defined in the diagram as those vectors. We defined C as this vector in the diagram. Then we stated all of this. We defined A and B. So you're right, but we've done that. And the diagram did part of that. And now this is true. And you said what I was looking for, the dot product is in here. Magnitude of A times magnitude of B times cos theta. Now there's a bunch of other junk involved, but isn't that useful? So guess what? We're going to take that to the other side. Sure looks like something we want to isolate. Oops. Oh, thank you. Any ideas what we do next? We divide by 2, did I hear that? We could do that now or we could do that later. I'm going to do it later because it's less writing. But you're absolutely right. We're going to do that eventually. I'm going to sub in those Cartesian vectors that we came up with. Remember, we have the magnitude of A. So what is the magnitude of A? And I have to square the whole thing. The magnitude of A was the square root of, and I'm going to write this the sort of lazy way now because it would be too much to write the whole thing all the time in brackets. So ax squared, ay squared, and since it's the magnitude of A squared, it's all of that squared. Is that okay? Same thing for B. Now what about C? Well, we define C. Where is it? There it is. So take a look. To find the magnitude of something, it's just like the horizontal component squared and the vertical component squared. So horizontal component squared, vertical component squared. These are now, this is a Cartesian vector. So these are no longer vectors. These are like coordinates, x coordinate, y coordinate, right? Like these are numbers. It's a horizontal component. Okay, so I can do this. So this is going to be the square root of, I do need brackets here, ax minus bx all squared plus, because this is C, ay minus by all squared, square root of all of that, all squared. Now what do you think we do? I think part of it is obvious. All the square roots cancel with the squareds. So it's going to be something like square root and square cancel. So I just get ax squared plus ay. Ooh, that doesn't really look like an a. Ay squared plus bx squared plus by squared. So these are going to cancel as well. But what about this junk in here? What do you think we should do? You all know what to do. You just don't want to admit it. Please don't tell me we have to expand all of those things. Yes, of course we have to expand all of this. It's not even that bad, my goodness. Of course we have to expand them. So ax minus bx all squared is ax squared minus 2ax bx plus bx squared plus ay squared minus 2ay by plus by squared. Not that bad. Now what? Requires a simple observation. You mean distribute the negative through? And what's that? How's that going to help us? All kinds of things are going to add to 0. Look at how many of them there are. Ax squared minus ax squared. I'm not even going to bother expanding. We can see that it's going to subtract, right? So we don't have to rewrite this whole thing. Ax squared minus ax squared. What else? Ay squared minus ay squared. That minus applies to everything in the brackets. Bx squared minus bx squared. By squared minus by squared. All 4 of those canceled. Now I'm going to distribute the negative through to what's left, which is just these 2 terms. They're already negative, so they're going to become positive. So it's 2axbx plus 2ay by. Remember what that equals? 2 times that. Mario, what do we do now? Divide out the 2's. And we have our formula. I'm just going to rewrite this. So if vector A, and I'm going to change up the variables. I don't know why, just because. A1, A2, and vector B is B1, B2, then A dot B is A1, B1 plus A2, B2. And this is so important, I'm going to put a box around it. An interesting way of thinking about this is I'm bringing together like parts. The x's go together, the y's go together. Do you see how that's true? Both x's are multiplied, here or here, however you want to look at it. Both y's are multiplied. So this is opposite to how the cross product works. And when we do the cross product, you compare how the cross product is the opposite to this. Dot product is comparing things that are the same.
If you say on the top what the magnitude of vector C equals, can we just sub in the A and B magnitudes instead of C and just cancel them out there?
I'm not sure I know exactly what you mean. Like if you defined this,
No, I mean, yeah, in terms of A and B.
what is it in terms of A and B? It's this.
So we have to write it.
Yeah, I don't think there's a shorter way of writing it. Okay, a couple of quick examples. We're almost done where we use this. Again, it's quite like that's an easy formula. You do need to memorize it though. You're not going to. I mean, if you just think, well, I'm multiplying like parts, x's with x's, y's with y's, add everything up, that's how it works. Remember that. Cross product is a bit more complex. It's still computationally fairly easy, although the numbers are a bit bigger. In the dot product, as long as you start with small numbers, I'm sure you can do it all in your head. With the cross product, even if you start with smaller numbers, sometimes it's a little bit harder to do in your head. But so we've got 2 vectors defined in Cartesian space. U is 4, -2. V is 5, 3. Find U dot V. U dot V will just be 4 times 5 plus -2 times 3. 20 minus 6, 14. See what I mean? Easy enough, right? Any questions? We'll do one more. I want you to do this one. Who's got it? What's the answer? 0. Everybody get 0? What does that mean? Right angle. Remember we talked about that? Right angle. Dot product 0, right angle. But take a look at that visual. Doesn't that make sense? When you look at those, don't they look like they're at a right angle? Of course, that's not enough to prove it, but it's true. Go all the way back to grade 9. Back in grade 9, how can you relate this to grade 9 and understand why those two vectors are at a right angle to each other? Any ideas?
It's just the same. It's just smaller. It's just smaller than this slope direct conditions.
Yeah, negative slope. What were you going to say?
I was going to say the slope of the actual line.
Yeah, very good. Think about the slope. Think about these as slope. Vectors have an interesting connection to that concept of slope in grade 9. This vector is over 2 up 1 over 2 up 1 over 2 up 1. I can scale it up or scale it down. Now, vectors have a magnitude. So it's not like slope in that way, but it's similar where I count, but it always has like the same quotation mark slope. And so if this is over 2 up 1 and this is over 1 down 2, they are negative reciprocal to each other. You could think of it that way. So it's very similar to slope. And you're going to see that even more and more in the next unit. Any questions?